Okay, so let's consider now flexure design. So suppose this is like the accelerometer that I showed at the very beginning of the lecture. Um, Here we have a clamped clamp flexure design. Here's where the proof mass is, or it says shuttle. So this can be moving up in the y direction, in the positive y direction. And you see the anchors here on the left and the right. And now this thing is drawn as having the beam width here is given as B, and the length of each flexure is given as L. And so when this thing moves, it's going to sort of, right, we're going to get a deformed shape where this shuttle has moved up by some amount. These guys can't move from their anchors, and so this deformed shape of the flexure will be sort of this S curve, okay, where it's straight here at the base, twisting in between, and then sort of the same thing on the other side. So there's really two springs that are acting on the two sides of this thing. And if we go back to the table here, well, this guided cantilever beam is what we have on the left side, and we have the same thing on the right side. And so we could write that it turns out we've got a spring constant of 4 kc on the left and a spring constant of 4 kc on the right. Four times the cantilever spring constant. So what are the advantage of this kind of spring? Well, it has a large stiffness ratio. So the ratio of the stiffnesses in the x and the y axes is basically equal to L over B squared. And so, for example, if L is 500 microns and the beam is 5 microns wide, well, that ratio is 100 to 1. So when we square it, we get a 10,000 to 1 ratio, right? So this is talking about the ratio of the stiffnesses like this in the x and the y directions, right? So this would be the directions that are important, for example, in terms of the snap-in instability, right? If we have comb drives and we want to move this thing in this direction and we don't want it to snap in the x-axis, then we have a 10,000 to 1 ratio of the stiffnesses. So this design, this sort of suspension is very good from that point of view. There are a couple of problems, though. It has a very small linear range. And so this is from this Legtenberg paper that I have in the references section of the Smart site. If you look over here, this is the y-axis displacement. He's calling this motion here delta y, so the small displacement of the y-axis. And he's plotting it here on the y-axis normalized by the beam width B is the way that I wrote it here. So this is B. Okay, and what we can see is here is the straight line. This is our equation that we would get if we use the cantilever spring constant that we calculated. Turns out that this is really only valid up to about here. This is delta y over B is equal to 1/4. Okay, so in other words, we can deflect about 1/4 of the beam width in the linear region, and then after that, the spring constant basically becomes sublinear. Okay, so this is the true nonlinear deformation. And so one question is, why does that happen? And we will solve that in a future lecture. We're going to use an energy method to calculate this nonlinear spring constant. The other thing is this design is very sensitive to residual stress, and so I talked a little bit about that in a previous lecture. What I want to motivate for you here is if we imagine, so we have something that's anchored to the wafer on the right and on the left, if we have a tensile residual stress in the material, then we're going to get still there's going to be these springs are going to be in tension, and so just like a guitar spring, they're going to be stiffer, right? When we have so the spring constant will go up. So if we have compressive stress, well, the main problem with compressive stress is we can actually get buckling of the flexure. So compressive stress is a problem. So this is a design where if we have stress variation from wafer to wafer, it's going to be very sensitive to that stress variation. We have very small linear range, and so usually this kind of design is not used. One solution is to use what's called a crab leg design, and again, this figure comes from the Legtenberg paper, and so if you want to see more analysis of this, then read that paper. But if we imagine now the deformed shape this thing. So now what we've done is it's got these straight lines here, but we have these little shins, is what he's calling it, the thigh and the shin. So what happens is that under deflection, the beam shape will sort of look like, I'm going to try my hand at drawing it, sort of look like this. Whoops. Sort of undershot where I need it to be. Okay, and I'm not going to try to draw the other side because I'm going to have trouble doing that. So the idea is that as this thing moves up in delta y here, this shin here can deflect by some little amount delta x. And the key thing is that, so we'll talk about this later on, the reason why this thing becomes nonlinear is clearly that when I've moved up by some distance delta y, I had, not only did I bend this beam, but I had to stretch it, because the length of this path, hopefully you can see from my drawing, this length here is shorter than this length here, so it had to be stretched. And so there's, in addition to bending, there's an axial tension, a tension along the axis of the beam that develops from motion. And that axial tension is what makes this thing nonlinear. Here, because the shin can bend, there's no stretching of this beam that's required. And so it has a much greater linear operating range. And the only drawback is that now we're going to, if we imagine that we push with a force in the x-axis, oops, not fy, fx here, right? If we have a force in the x-axis, this thing can move, okay? It will move over because the shins can bend. And so this is not good. Okay, so in terms of like the instability of the comb drive is going to be much worse for this design. A better design is what is called a folded flexure, and this is also called a truss sometimes, truss suspension. So I'm going to show again here we have our deflection this way. Here's the anchors, and so what happens is that this thing can move along in the middle, move up like this, and what happens is that this part will also translate, and it has a fairly linear operating region, because as these things, as these springs move, as they are flexed, this thing can move inwards. Okay, so we have less problem with axial tensioning. Now, because the beams are still straight and this truss is very thick, so we make it thick in this direction. This is the truss part here. So we want this thing to be very stiff, and so we have a very large stiffness for forces in the x-axis pushing along this direction, and also pushing up and down. And most of the residual stress can be released. So there is, so basically, if we imagine that this thing is in compression, when it is released from the wafer, these beams can extend, and it's only this part sort of between where the anchors are that will still be in compression. So we reduce the residual stress by a large amount. So all of this section here is free to expand, and it's only the region in between the anchors that cannot expand. And hopefully you can see that that's true by reasons of symmetry. Okay, now I'm going to calculate actually what the spring constant of this folded flexure design is. So what you'll see is basically it's symmetric. We have one spring on the left, one spring on the right. We're going to break them into pieces and analyze them using the cantilever beam approach. So I'm going to start with one of the beams in this flexure here, so just looking at one of them. Now it turns out that this truss can't rotate, and the reason why that's true is, again, it's sort of symmetric. If we cut it in the middle here, that things are the same on the left half and on the right half, or the top half and the bottom half, and so it's clear that there's no rotation of this thing. And so if we look at one beam, then we could analyze it as being basically clamped on the left side and guided along here. Okay, so there's no slope at this end. And further, if we look at the shape of this beam, we can see again by symmetry that it really looks like if we could cut it in half. And there's a cantilever on the left and a cantilever on the right. So this is what's called a fixed guided beam. And it really is the same thing as two cantilevers that are in series. And springs in series, well, they have the same load across them. So if I have a force F here on the right-hand side, well, I would, if I cut it here, I'd still have to put that force F here. So these two springs have the same load, but their deflections will add. So there's a little bit of deflection from the first half, and then a little bit of deflection from the other half. And by symmetry, I hope you can see that those displacements are equal. So we get basically the same load, and we have twice the displacement. And so if we write the equation for, and what I'm saying here is that the total length of this cantilever is twice the length of these individual cantilevers. Okay, so L is the true length of this beam, and we're going to call that twice the length of the cantilever. So if I write what the cantilever spring constant is, it's EWH cubed over 4L cantilever cubed. And so I can substitute in, well, that the cantilever length is half the length. So I get Kc is equal to EWH cubed over 4L over 2 cubed. And so when we simplify this, we get EWH cubed over L cubed. And the springs in series have the same load and their deflections add. So we don't, for springs in series, we don't add their spring constants, we add their compliances. So 1 over K for the spring is equal to 1 over Kc plus 1 over Kc. So we could write that 1 over K is equal to 2 over K cantilever, or similarly we could write that the spring constant of the fixed guided beam is equal to 1/2 Kc. Okay, so the way that you can think about this is that really what we're doing is where the compliance of this beam is equal to the compliance of the cantilever plus compliance of the second cantilever. So when we add springs in series, we add their compliances. Okay. And so what we get is that the spring constant for this fixed guided beam, we're going to put these two things together, is going to be equal to EWH cubed over 2L cubed. Okay, so hopefully that makes sense. And let me make sure that I did that right. Oh, let's see, I missed a factor of 2 here. So K cantilever is going to be 2. There's 2 here, and so when I take the 1/2, I get this. So sorry. So this is the actual the actual answer. And so if we look back at the table, hopefully that agrees with what's in the table. It should. Here it is in the table. Okay, so the fixed guided cantilever beam has EWH cubed over L cubed, or 4 times the stiffness of the cantilever beam. Okay. So that's the right answer. So this is a series combination of cantilevers. Now if we look at the suspension, we can see that there's actually 2 of these that are in parallel. And so we have springs that have the same displacement. The load is shared, and the spring constant is the sum of the individual spring constants. Okay, so now we have springs in parallel. Springs in parallel add. So we get the spring constant for this is equal to K for the spring A plus K for spring B. And we could write it as 2 times k for the fixed